Hello, my name is Christian Brommer. I'm a PhD student at the University of Klagenfurt, and I'm presenting our work on improved state estimation in distorted magnetic fields. First, I want to talk about the problem definition and what's missing in the state of the art. Magnetometers are helpful in determining the orientation of a vehicle, but the use of this information is not always straightforward. For instance, the magnetic field of the Earth varies naturally or caused by man-made structures. This can affect the magnetic field in direction and magnitude. Because of this, advanced estimators include the variation of the local magnetic field in the state vector. This is interesting for both long-term UAV flights in which the magnetic field varies naturally or in local areas in which disturbances are introduced by the environment. The classical state-of-the-art approach makes use of Cartesian coordinates to express the magnetic field. However, this representation suffers from observability and consistency issues. We are introducing a new approach that defines the update of the magnetometer in spherical coordinates, which is a more natural representation. The measurement of a magnetometer represents an orientation in 3D and the magnitude of the magnetic field, which is independent of the orientation. Therefore, a representation of the measurement in Cartesian coordinates is rather unintuitive since the information of orientation and magnitude are combined in values for x, y, and z. The spherical representation is the much more natural choice, and we will show that the representation in spherical coordinates improves the robustness and disturbance detection of the estimator. We will also show that the representation in spherical coordinates improves the signal characteristics for the use of filters that rely on the assumption of Gaussian distributed signals. In addition, we will show that the spherical representation has benefits for observability and that the spherical approach introduces less nonlinearities. The reduction of nonlinear components for the sensor model is highly desirable and improves performance, especially for consistency. This ensures uninterrupted state estimation and improved detection of outliers by reducing false positives and allowing a reliable and dynamic adaptation to disturbances. This slide shows the comparison of the Gaussianity for the two coordinate representations. We are using QQ plots, which show the expected number of samples of a Gaussian hypothesis with the red line and the recorded static measurement samples with blue dots. The way in which to interpret a QQ plot is straightforward. The closer the measurement samples match the expected number of samples, the closer is the signal to the Gaussian hypothesis. We displayed the Cartesian measurements for x, y, and z on the top, and the measurements for spherical coordinates, meaning azimuth, elevation, and magnitude, on the bottom. First, we notice that the Cartesian measurements are clustered, which is caused by the discretization of the original measurement. The conversion to spherical space shows less discretization due to the transformation. However, besides the discretization, the Cartesian measurements are strongly offset with respect to the hypothesis, while samples in spherical form match the hypothesis much closer. Based on this, we can determine that the measurement representation in spherical coordinates is more Gaussian distributed compared to the Cartesian representation. This is beneficial for filters that rely on Gaussian signal characteristics, such as extended Kalman filters or unscented Kalman filters, for example. The next aspect is the observability of the system. Our system definition introduces the vehicle's navigation states with position, velocity, and orientation of the vehicle's body in the world, as well as IMU biases. We are also expressing the magnetic vector, which incorporates the magnetic inclination and declination with respect to the world frame. In addition, we also introduce an orientation calibration of the magnetic sensor with respect to the IMU. For this system definition and IMU-driven state dynamics, the state for the calibration of the magnetometer, QIM, is observable. However, the magnetic variation and the orientation of the magnetometer in the world are jointly unobservable. These states can be rendered observable if a position update is incorporated, which would contribute the so-called pseudo-attitude. However, our focus relies on the system definition with a magnetometer only. The table on the top shows the observability analysis for the magnetometer in Cartesian representation. Here, we can see that all components are jointly unobservable. The table on the bottom shows the observability analysis of the system with the spherical sensor update definition. This shows that the orientation components are still jointly unobservable, but the magnitude of the magnetic variation is fully observable. Changing the representation of the measurement does not change the observability of a system per se, but the spherical form allows a clear interpretation and provides the magnitude as a direct measurement which benefits the consistency of the filter. To validate this result, we generate a synthetic dataset with Cartesian measurements and introduce wrong initializations for the magnetic vector. The top graph illustrates that the error of individual components does not converge. However, the graph on the bottom shows that the error of the post-calculated norm for the same data does converge. Our goal is to detect disturbances in the magnetic field. Because of this, we are using the magnetic field strength and corresponding outlier as a measure for the change of the magnetic field. Therefore, it is important to have reliable outlier detection for the state. This slide shows another benefit of the spherical representation. Here, we are using the same dataset for the three scenarios to validate the reliability of the chi-square detections, which in turn validates the estimated covariance. The chi-square test is set up to reject outliers outside the 3 sigma bound, and we expect a rejection rate of 0.3%. The first case performs the chi-square test on the residual for the individual Cartesian coordinates. We can see that the chi-square test detects 0.18% as outliers, showing that the filter is underconfident. The second case shows the result for the spherical sensor update definition with the chi-square test performed on the estimated magnitude. The rejection rate for this scenario is at 0.24%, which is close to the expected value of 0.3%. The third case performs the chi-square test on the norm of the Cartesian states. The results show that the filter is overconfident because of the high rejection rate of 1.2%. Therefore, it can be said that the spherical definition provides a more accurate covariance estimate, which results in less false positives for the chi-square test. Now that we are able to detect outliers in the magnetic field reliable, we can go one step further and perform a correction step in the event of a magnetic disturbance. The graph on the bottom shows the correction of the covariance. We define a magnetic disturbance by a sequence of 10 consecutive outliers for a 3 sigma bound. This is indicated by the blue 1 sigma probability density function and the measurement at 3 sigma on the right. We are using the Jacobian of the spherical update definition and the chi-square upper critical value to enclose the disturbance by 1 sigma. This is shown by the orange probability distribution. The error plot of the magnetic field strength on the top right shows the result. A disturbance is introduced at t equals 300 seconds. The covariance is increased after 10 consecutive outliers, and the error, as well as the covariance, converge within 1 second. We would need to calculate a 3x3 covariance matrix based on the scalar chi-square value if we want to perform the same method for the Cartesian case. However, this would require solving a one-to-many problem. The spherical definition has the benefit that the update of the magnitude is direct and independent of the rotation, as can be seen by the measurement Jacobian on the top left. Now we are applying this approach to real-world measurements. We use a trajectory of about 1000 meters to compare the newly introduced approach to the classical version. This data was recorded at an outdoor parking lot. The dataset consists of RTK position information and magnetometer measurements. However, the position information is only used to associate the detection of disturbances to a certain location. The trajectory is marked in blue, and the green dots indicate individual disturbance detections. As mentioned before, disturbance detections can be true outlier or actual disturbances in the environment. Thus, we decide that 10 consecutive disturbances, or much more outlier detections, represent an actual disturbance, which triggers a covariance adjustment such that the current state can converge to the new magnetic environment. The overlay of disturbances with the trajectory showed two interesting points, as shown in the graph. The next slide will show the magnetic strengths for the periods that overlay with these position segments. This is the signal progression for the full dataset. The purple signal represents the measured strength of the magnetic field, and the blue signal is the filtered signal for the Cartesian definition. The chi-square detections are shown with red dots on the top of the graph, and covariance adjustments are shown with blue dots. The plot on the bottom shows a zoom segment on the region indicated with the red circle. The signal segment coincides with the two positions we have seen in the trajectory. We can see that the filter is overconfident, which causes numerous false positive detections and covariance adjustments. As a result, the state of the filter follows the measurement closely. In contrast, this slide shows the results of the proposed spherical definition. We can see that the rate of rejection is closer to the value we would expect for a 3 sigma bound, and the filter is slightly underconfident. Now, while looking at the zoomed segment of the plot, we see multiple outlier detections, but only 4 covariance adjustments that coincide with the actual disturbances associated with the locations in the trajectory. This allows the estimator to perform accurate filtering of the information, and the state does not follow the noise of the signal as it was the case for the Cartesian definition. To summarize the presentation, we first looked at the signal characteristics and determined that the spherical representation of the magnetic field is more Gaussian distributed. We then looked at the system's observability and determined that a spherical representation renders the magnetic field directly observable. We could then confirm that the spherical definition is more consistent based on 3 cases with chi-square detections. The next step was the introduction of the covariance adjustment, which allows the state to converge to a new value after a disturbance was introduced. And at the end, we applied the classical approach and the newly proposed approach with spherical updates to real-world data. We confirmed that the spherical approach outperforms the classical approach in terms of robustness. Thank you for your attention.